Hello, you are at Spatium, right now, while you are sitting still on Earth. Our entire planet is actually rushing through the universe at millions of kilometers per hour towards something enormous that we can barely see. And today's story will take you on a journey to explore that mystery. Right now, while you are sitting still, listening, or simply resting in a quiet room, Earth is not standing still the way our senses might suggest. The entire planet is racing through space at about 1.4 million miles per hour, heading towards something gigantic, a mysterious, invisible gravitational source hidden behind our own galaxy. You have never felt that motion, and you probably never will. For most of human history, we did not even know it was happening. But modern astronomical observations show that not only Earth, but more than 100,000 galaxies in the vast region of space around us are also drifting in the same direction, being pulled toward a gravitational source so large it is almost impossible to imagine. Strangely, this source lies behind a thick wall of cosmic dust within the Milky Way itself, preventing us from observing it directly with ordinary telescopes. Astronomers call this mysterious structure the Great Attractor. It is related to enormous cosmic structures such as the Shapley Supercluster, and it may even be influenced by gigantic cosmic voids that push galaxies from behind. The strangest part is that although we are moving toward it at an astonishing speed, it is possible that we will never actually reach it. To understand why this happens, the story must begin with something older than every star or galaxy, the oldest light in the universe. Before talking about the enormous gravitational forces pulling entire clusters of galaxies through space, let us begin with something closer to home. Right now, you are moving. You do not feel it. The cup of coffee on the table is perfectly still, and the room seems completely quiet, with no sign of a massive motion taking place. But in reality, Earth is orbiting the Sun along a path about 600 million miles long every year. When we calculate the speed from that orbit, we obtain a figure of about 67,000 miles per hour. That means every hour our planet travels tens of thousands of miles through space without ever stopping. We cannot feel this because everything around us, the atmosphere, the oceans, the land is moving together with Earth. This principle is exactly the same as when you sit in a car cruising smoothly along a highway. Inside the car, you do not feel strong winds or any large shift in position, because everything inside the car is moving at the same speed as you. However, Earth's motion around the Sun is only the first layer in a chain of much larger motions. The entire solar system is also orbiting around the center of the Milky Way galaxy. This orbit is so enormous that it is difficult to imagine. To complete one full rotation around the galaxy, the solar system needs about 225 million years. That means the last time we were at this same position in our galactic orbit, Earth was still in an era when the earliest ancestors of dinosaurs were just beginning to appear. To maintain that enormous orbit, the solar system must move at about 500,000 miles per hour, 500,000 miles per hour, and still we feel no motion at all. But the story does not end there. Even the Milky Way galaxy itself is not standing still. Our galaxy, together with Andromeda, the Triangulum galaxy, and about 50 smaller satellite galaxies, forms a gravitational cluster called the Local Group. This group of galaxies is also moving through the universe. Scientists measure that motion by comparing our position with something very special, the cosmic microwave background radiation, the light left over from the moment the universe was first formed, about 380,000 years after the Big Bang. The temperature of the universe dropped low enough for electrons and protons to combine into neutral atoms. For the first time in the history of the universe, light could travel freely through space without being scattered by plasma particles. That light spread out in every direction, over billions of years. As the universe expanded, its wavelength was stretched, and today we observe it as microwave radiation. This ancient light fills the entire sky, arriving from every direction at once. We call it the cosmic microwave background. Interestingly, humans did not discover it through a grand research plan, but almost by accident. In 1965, Two engineers at Bell Labs, Arno Penzias and Robert Wilson, were testing a radio antenna designed for satellite communication. No matter which direction they pointed the antenna in the sky, they heard a faint but persistent noise. Like a soft hiss in the signal, they checked every component of the equipment, cleaned the antenna, and even removed a pigeon nest from inside the receiver system. But the noise would not disappear. Eventually, they realized the signal was not a malfunction of the equipment. It was the leftover heat from the birth of the universe. This discovery later earned them the Nobel Prize in Physics in 1978. At first, the cosmic microwave background appeared completely uniform, with a temperature of about 7 Kelvin above absolute zero. But as measurement instruments became more precise in the 1970s, scientists discovered a tiny but extremely important detail. The temperature of the background radiation is not exactly the same in every direction. One half of the sky is slightly warmer, while the other half is slightly cooler. This difference is extremely small, only about 1 part in 1,000, and is called the temperature dipole. Small as it is, it carries an important piece of information. We are moving. When an object moves through a medium filled with waves, the waves in front of it become compressed, while the waves behind it are stretched out. This phenomenon is similar to the Doppler effect that we hear when an ambulance passes by. The sound becomes higher in pitch as it approaches and lower as it moves away. The same thing happens with the cosmic microwave background. If our entire galaxy system is moving through space, the light in the direction of motion will appear slightly hotter, while the light behind us will appear slightly cooler. Exactly this effect has been measured. From this data, physicists calculate that the local group is moving at about 630 kilometers per second, equivalent to about 1.4 million miles per hour. In the time it took you to hear a single sentence, everything you have ever known, Earth, the solar system, and even the Milky Way galaxy has already moved tens of kilometers through space. But what truly made scientists curious was not the speed, but the direction of that motion. If the universe were simply expanding uniformly, galaxies would drift away from each other in all directions. But the motion of the local group points directly toward a specific region in the southern sky. That means somewhere in that direction there must exist an enormous structure creating a gravitational pull strong enough to draw galaxies toward it. To investigate this, in 1980, 7 astronomers began an ambitious project to measure the true velocities of galaxies. The group included Sandra Faber, Alan Dressler, Donald Lyndon Bell, David Burstein, Roger Davies, Roberto Turlevich, and Gary Wegner. Later, they became known by a famous nickname in astronomy, the Seven Samurai. Their goal was to measure the peculiar velocities of galaxies, not the motion caused by the expansion of the universe. To do that, they needed to measure precise distances to hundreds of galaxies and compare them with the observed velocities. They developed a technique called DN sigma, based on the relationship between the motion of stars in elliptical galaxies and the true brightness of those galaxies. Over many years of telescope observations, they collected data from hundreds of galaxies in the vast region of space surrounding us. When they analyzed the results, they noticed something surprising. The galaxies were not moving randomly. Hundreds of galaxies across a region, hundreds of millions of light-years wide, were drifting in the same direction. Like leaves being swept along by the same current of water. Their speeds were between about 600 and 700 kilometers per second, and all of them were heading toward the same region in the southern sky. In 1986, they announced their conclusion: there must be an enormous mass of matter in that direction, creating a gravitational pull strong enough to draw the galaxies toward it. They called it the Great Attractor. However, the scientific community did not fully accept this conclusion at the time. According to widely accepted cosmological models, on very large scales, matter in the universe should be distributed relatively evenly. There should not exist a single structure large enough to control the motion of such a vast region of galaxies. Some scientists suspected that the group's measurement methods might contain systematic errors, or that the data could be biased. But despite the debate, the data from the Seven Samurai continued to point to the same phenomenon. A galactic flow was present. The biggest problem at the time was that no one could actually see the object creating this gravitational pull. The reason lay in its position in the sky. There is a wide band stretching across the sky along the plane of the Milky Way galaxy that contains enormous amounts of cosmic dust. This dust absorbs and scatters visible light so strongly that optical telescopes can barely see through it. Astronomers call this region the zone of avoidance. About 20% of the observable universe lies behind this band of dust. Ironically, the location of the Great Attractor lies almost exactly within that region. This made scientists feel as if they were trying to find a gigantic object hidden behind an impenetrable wall. They knew it was there because the surrounding galaxies were moving toward it, like ships drifting toward a whirlpool in the ocean. But the whirlpool itself was completely hidden. For many years, all estimates of the mass of the Great Attractor were based solely on the motion of the galaxies around it, leading to very different results. Some estimates suggested it was large but still within a reasonable range. Others suggested it was so enormous that it seemed almost unbelievable. The breakthrough only came when astronomers decided to abandon visible light and observe the universe using X-rays. Unlike ordinary light, X-rays have much higher energy and can penetrate cosmic dust much more easily. If a gigantic cluster of galaxies existed behind the wall of dust, the extremely hot gas between those galaxies would emit strong X-ray radiation. In 1990, the German satellite, Rosat, was launched into orbit and conducted the first all-sky X-ray survey. When researchers examined the zone of avoidance using X-ray data, they discovered hundreds of galaxy clusters that had never been seen before. Subsequent surveys, especially the CIZA program clusters in the zone of avoidance, identified more than 200 galaxy clusters hidden behind the Milky Way's dust. Among them, one cluster stood out in particular, the Norma Cluster, also known as ACO 3627, located about 220 million light-years away, almost exactly behind the galactic plane. This cluster contains thousands of galaxies and an enormous amount of matter. For many astronomers, the Norma Cluster appears to be the heart of the gravitational region we call the Great Attractor. However, this discovery turned out to be only part of the story, because as scientists continued to study the region more deeply, they began to realize that the gravitational pull guiding our motion might not come from a single structure, but from an immense network of superclusters of galaxies spread across the universe. Subsequent X-ray observations revealed many important details about the Norma Cluster. The data showed that this is indeed a gigantic structure, containing thousands of galaxies and an enormous amount of superheated gas between them. The extremely high temperature of this gas is a sign that the cluster's gravitational field is very deep, because only in environments with extremely strong gravity can gas be compressed and heated enough to emit such intense X-rays. When astronomers estimated the mass of the Norma Cluster, they arrived at a figure of about 10 to the power of 15 times the mass of the Sun. In the language of cosmology, that is a truly massive galaxy cluster. For a short time, many researchers believed that the mystery had finally been solved. Before that, the Great Attractor had often been described as a single, gigantic object hidden behind the dusty region of the Milky Way. Norma was also a large structure located exactly in that position, concealed behind the zone of avoidance. So many people quickly assumed that Norma was the Great Attractor, or at least its central core. But when scientists began to calculate more carefully, everything became more complicated. The mass of Norma is large, but not large enough to explain the full velocity that the surrounding galaxies are displaying. The gravitational pull from a galaxy cluster with a mass of about 10 to the power of 15 solar masses at that distance would produce a certain flow of motion, and that flow can be calculated quite accurately using gravitational models. When researchers compared those calculations with the observational data, they realized that Norma's gravitational pull could explain only part of the motion of the galaxies in the region. It could contribute to the velocity that the local group has, but it could not explain the full value that surveys had measured. This forced cosmologists to change the way they imagined the Great Attractor. Instead of being a single gigantic object, it gradually came to be understood as a vast gravitational region, a basin of attraction where matter in the universe is concentrated more densely than average. Within that basin, Norma is the largest structure we know of, but it is only one node in the network, not the only center. The entire region is more extended, more diffuse, and not dominated by a single galaxy cluster in the way people had once imagined. This discovery created a significant setback for the one giant object model. What many people had imagined as a monstrous galaxy cluster, when observed in X-ray light, instead appeared as a collection of several moderately large structures within a region of higher than average matter density. But this in turn opened up a more difficult question. If Norma and the entire gravitational basin of the Great Attractor were still not enough to explain the velocity we observe, then what else was contributing to this motion? There had to be another gravitational source, much farther away, a structure that cosmologists had previously assumed was too distant to have any significant influence. That structure had actually been known for a long time. It had been catalogued in astronomy for decades, but until recently, almost no one thought it had anything to do with the motion of our galaxy. The story of that structure begins in 1930, when the British-American astronomer Harold Shapley discovered a region in the sky in the constellation Centaurus containing an unusual number of galaxies. This was a very distant area, so distant that for many decades cosmologists regarded it only as an interesting curiosity on galaxy maps, a large galaxy cluster lying at a great distance, perhaps unrelated to the dynamics of the region of space where we live. But that assumption was later shown to be significantly wrong. The structure that Shapley discovered is now called the Shapley Supercluster, a gigantic supercluster of galaxies located about 650 million light-years from Earth, about 4 times farther away than the Great Attractor region. In cosmology, distance usually means gravitational influence decreases rapidly. According to the law of gravity, attraction decreases with the square of the distance. If an object is 4 times farther away, its gravitational pull at our location will be 16 times weaker than an object of the same mass that is closer. This means that for Shapley to affect the motion of galaxies near us, it must have an extraordinarily enormous mass. And in fact, that is exactly the case. The Shapley Supercluster contains more than 8,000 individual galaxies, and its total mass is estimated at about 5 times 10 to the power of 16 times the mass of the Sun. Written out fully, this is equivalent to 50 quadrillion times the mass of the Sun. This is one of the largest gravitational structures within a few billion light-years of Earth. Throughout most of the 20th century, the common view remained that Shapley was too distant to have a significant effect on the motion of the local group. Scientists believed that the nearer Great Attractor region was the main gravitational source, while Shapley was merely part of the background structure of the larger cosmos. But astronomical surveys beginning in the mid-2000s gradually broke down that assumption. When researchers analyzed the motion vector of the local group more precisely, they realized that the flow of motion does not stop at the Great Attractor. If the Great Attractor were the only cause, the direction of our velocity would point straight toward its center, and the flow of surrounding galaxies would also converge entirely there. But the velocity maps showed something else. The flow continued past the Great Attractor and extended farther still, toward Shapley. Many independent analyses confirmed this. When scientists compared the motion of the local group with the gravitational map of both structures, the Great Attractor and Shapley, they realized that both are contributing to the velocity we observe. Although Shapley is much farther away, its enormous mass compensates for that distance, making its gravitational influence nearly as large as that of the Great Attractor. This carried major significance. Throughout most of the 20th century, cosmologists had tried to explain our motion using a single gravitational source, but when Norma was found to be smaller than expected, the velocity budget remained incomplete. Shapley, at a distance of 650 million light-years, was providing an important part of that missing pull. The picture of the universe, therefore, became literally larger. The gravitational forces shaping Earth's path are not confined to nearby space, but extend across hundreds of millions of light-years. This idea can be overwhelming, because it shows that the factors determining the direction of our planet's motion lie at distances that humans once thought were completely irrelevant. However, even when combining the influence of the Great Attractor and Shapley, the numbers still did not match perfectly. At the same time, the initial estimates of the Great Attractor's mass were about to be revised in a way that made many researchers reconsider the entire picture. In science, being wrong is sometimes part of the process of progress. Hypotheses are proposed, new data appears, and in the end, the data itself decides what is correct. The Seven Samurai group had spent years building their argument using the best distance measurement techniques of the 1980s. Their core discovery that galaxies were drifting along a common flow remained completely correct. But the mass estimate they assigned to the Great Attractor was not correct. The initial figures were very large, with many estimates placing the mass of the Great Attractor at several times 10 to the power of 16 solar masses or more. These numbers seemed reasonable at the time, because they were necessary to explain the observed velocity if the gravitational source lay at the predicted distance. But when X-ray surveys in the early 2000s mapped the galaxy clusters in this region in detail, the actual picture became clearer. Norma was the largest structure, with several additional clusters around it, but none of them were truly extraordinary. When scientists summed the mass of all the galaxy clusters in the Great Attractor basin, they realized that the total actual mass was much lower than the initial estimates. This revision was not a minor error. The new figures showed that the true mass of this region was about 90% lower than what had once been published, that is, off by nearly an order of magnitude. The scientists who had doubted the scale of the Great Attractor turned out to be partly right. Within the scientific community, the reaction was fairly familiar. Those who had been skeptical saw this as evidence that earlier estimates had exaggerated the size of the structure. Research papers that had relied on the old figures quietly updated their data. The Seven Samurai faced a situation familiar in science. They were right about the important discovery, but wrong about the detail that had made that discovery seem more dramatic. What mattered was that the core of their discovery still stood firm. The galactic flow is real. Hundreds of galaxies are moving toward the southern sky at speeds of hundreds of kilometers per second. The Great Attractor region truly exists as an area of higher than average matter density in the universe. The Norma Cluster is real. That gravitational basin is also real. The only thing that collapsed was the idea that a single structure could explain all of this motion. The mass revision forced cosmologists to look farther out. It made the Shapley Supercluster a central factor in the picture, and it led to a new conclusion. The velocity of the local group is not the result of a single gravitational source near us, but the combined influence of many enormous structures spread across hundreds of millions of light years. The story of the Great Attractor therefore changed. Instead of a simple answer, it became a complex gravitational network, a single giant object transformed into an entire system of interconnected gravitational forces. And at that time, the tools to fully map this system still did not exist. Building those tools would require enormous observational datasets, gathered by scientists on opposite sides of Earth, in one of the most ambitious projects in the history of cosmological research. What they built afterward not only helped clarify our motion through the universe, but also gave the Milky Way something this galaxy had never truly had, in an official sense, an address in the universe. To map how galaxies truly move through space, astronomers had to solve a highly complex, multi-layered measurement problem. When we observe a distant galaxy, we can measure how fast it is receding from us. But that velocity is always a combination of two different factors. One part comes from the general expansion of the universe, which is causing all large structures to move farther apart. The other part is the peculiar velocity of that galaxy, meaning its actual motion under the influence of local gravity. To isolate this true motion, scientists need an independent measurement of distance. Once they know the recession velocity and the true distance, they can subtract the part of the velocity that should exist because of Hubble's law, and the remainder is the peculiar velocity, the true trace showing in which direction the galaxy is being pulled by the surrounding gravitational landscape. In theory, that sounds neat and tidy, but when it must be applied to thousands of galaxies scattered across hundreds of millions of light years, it becomes a colossal task. almost one of the most ambitious mapping projects cosmology has ever pursued. In the early 2000s, Brent Tully at the University of Hawaii and Hélène Courtois at the University of Lyon began building exactly that kind of dataset. Their project was called Cosmic Flows. The goal was very clear, but also extremely large, to create the largest and most accurate catalogue of galaxy distances and peculiar velocities ever assembled, and then use that catalogue to reconstruct the gravitational velocity field of the region of the universe around us. The first generation of the project laid the methodological foundation and proved that this approach could work on a large scale. Then Cosmic Flows 2 greatly expanded the scope of the effort, collecting data from more than 8,000 galaxies and creating a true leap forward in both coverage and precision. Later versions, such as Cosmic Flows 3 and Cosmic Flows 4, went even further, incorporating tens of thousands of galaxies within a much larger volume of space. What they were reconstructing, in essence, was a map showing how gravity is organized in our cosmic neighborhood. Where matter is densely concentrated, velocity flows converge inward. Where matter is sparse, galaxies tend to flow outward, as if moving away from hollow depressions. The velocity field, therefore, resembles contour lines on a topographic map, except that this is the topography of an invisible landscape created by matter and gravity. In other words, Tully and Courtois were gradually creating a gravitational atlas of the universe around us. As that map began to take shape, it revealed something surprising. The flow patterns they observed did not simply converge toward a few isolated attractor points, as people had once thought. On the contrary, they were organized on a much larger scale. The velocity flows traced continuous structures, regions where the motion of thousands of galaxies was interconnected, as if all were drifting together within a shared gravitational basin. From that, the picture of the universe's gravitational geography became far more clearly layered than previous understanding had suggested. Individual galaxy clusters lay inside larger superclusters. Those superclusters in turn lay within even broader gravitational basins. The local universe did not appear as a random collection of disconnected clumps of matter, but more like a nested architecture, where flows and attractor centers operate simultaneously on multiple levels. Tully and Courtois were not merely measuring the velocities of galaxies, they were tracing the invisible skeleton of the universe around us. In the Cosmic Flows 2 data, one structure emerged that was too large to be dismissed as a secondary detail. It was too coherent, too consistent, and massive enough to require its own name. That result was published in 2014. And it gave the Milky Way something entirely new, an official position within a structure far larger than anything we had previously been accustomed to naming. On September 4th, the journal Nature published a paper led by Brent Tully. The paper was built around more than 8,000 galaxy peculiar velocities in the Cosmic Flows 2 dataset, and its conclusion was striking. The Milky Way belongs to a unified gravitational superstructure about 520 million light-years across, containing more than 100,000 galaxies and having a total mass of around 10 to the power of 17 times the mass of the Sun. They named this structure Laniakea, derived from Hawaiian with a meaning close to immense, boundless heaven. What the paper truly demonstrated was not simply the discovery of a new supercluster, but a different way of understanding how galaxies are linked by motion. The research team defined a basin of attraction based on the flows themselves. If the peculiar velocities of all galaxies in a region ultimately point toward the same gravitational center, then all those galaxies belong to the same basin, even if they are currently separated by hundreds of millions of light-years. To determine the boundaries of such basins, the team applied a watershed algorithm, similar to how people analyze topography on Earth to identify river basins. Each galaxy is like something drifting downhill in an invisible gravitational landscape. By tracing the direction in which they drift, one can construct the dividing walls between basins, and from that analysis, Laniakea emerged as a single basin of enormous scale. The Milky Way lies within Laniakea, the Great Attractor region, specifically the area around the Norma Cluster, lies near the gravitational core of this structure, the Shapley Supercluster. Meanwhile, is located beyond the far outer edge of the basin, outside the defined structure, but still adding gravitational pull from beyond. The significance of this discovery took time for both the scientific community and the public to fully absorb. The Milky Way had always been inside Laniakea. The discovery did not create a new structure, but rather provided a new way to recognize a structure that had always existed, had always surrounded us, but had never before been identified as a unified entity with a name. For a long time, the largest familiar context for the Milky Way had simply been the local group, a few dozen galaxies within roughly 10 million light-years. Looking farther out, we often referred to the Virgo Supercluster as a loose collection of multiple galaxy groups. But Laniakea swallowed the Virgo Supercluster within itself and showed that Virgo is only a small part of a much larger gravitational basin. The feeling is like previously only knowing your city, then your country, and suddenly discovering that you actually live on an entire vast continent that had never before had a name in common awareness. This discovery quickly captured public attention because it offered something very concrete and easy to feel a cosmic address. Milky Way, local group, Laniakea, a hierarchical chain placing our galaxy within a structure 500 million light-years wide. But within the scientific community, what drew attention was not only the new name or the new address. What many popular articles overlooked was a much more important detail in the data. After Laniakea was mapped, the velocity problem of the local group seemed to be largely explained. The Great Attractor region, together with the Shapley Supercluster, explained most of our motion of 630 kilometers per second. Most, but not all. There was still a small residual part of the velocity that remained incompletely explained. It was not large enough to be shocking. Only a few tens of kilometers per second left over after all the calculations. But in cosmology, a few tens of kilometers per second is not an error that can simply be ignored. It is a signal. It was precisely this small but persistent residual that suggested the picture was still missing one piece. And strangely, that missing piece did not lie where astronomers had once thought they would have to look, that is, it was not another gigantic mass of matter waiting to be discovered somewhere in the sky. A team, led by Yehuda Hoffman at the Hebrew University of Jerusalem, approached the cosmic flows, 2 dataset, along a different path. They used a mathematical technique called Wiener filter reconstruction, a method that makes it possible to infer the entire underlying matter density field from the measured peculiar velocities, even in regions where observational data are sparse or nearly absent. In other words, instead of looking only at what had been directly measured, this technique attempted to reconstruct the most complete gravitational picture possible from the velocity traces left behind by galaxies. And that reconstruction revealed something unexpected. It did not discover a new attractor, nor did it find another massive supercluster in some unmapped corner of the sky. What stood out instead was an absence, a region of space with a significantly lower matter density than the average of the universe. A gigantic void, a deep emptiness, lying in almost the opposite direction from the Great Attractor. If the Great Attractor pulls us from one side, then a very large underdense region on the other side would cause galaxies to tend to move away from it, thereby adding another velocity component that pushes us in the opposite direction, which also contributes to sending us rushing toward the Great Attractor. 2 mechanisms, 1 combined motion. That empty region is pushing almost as strongly as the dense gravitational region is pulling. This completely reversed the mental model that astronomers had been using for many decades. The story of the Great Attractor had always been told as a story about heavy things pulling us in large galaxy clusters, enormous superclusters, regions with too much matter. The question had always been, what has enough mass to pull us this strongly? That way of asking the question implicitly assumed that our motion was entirely the result of being drawn toward dense regions, but it turns out that this understanding was only half correct. The other half comes from the fact that we are moving away from an unusually matter-poor region. The direction of the local group's motion is shaped not only by what lies in front of us, but also by what does not lie behind us. That void had long been hidden in the data, but only when the velocity field was reconstructed with sufficient accuracy and sophistication did it emerge clearly. And once researchers realized that our velocity problem required both an attractor and a repeller, the entire explanatory framework for where we are going changed. The story of the Great Attractor did not end. It simply became more layered, more complete, and far harder to simplify. In 2017, Yehuda Hoffman and his colleagues published results that changed that perspective decisively. What they found was not more matter, but less matter. They called this new structure the dipole repeller. Almost directly opposite the Shapley Supercluster in the sky was an enormous region containing far fewer galaxies than average. Fewer galaxy clusters. Fewer of everything. It was a cosmic void stretching about 700 to 740 million light-years from our position. It was not a place where galaxies were crowding together, but a region left behind over billions of years as matter in the surrounding areas gradually collected into denser structures. And that emptiness, it turned out, also has very real gravitational consequences. If you think about gravity in a slightly different way, you can see why. Mass pulls objects toward it, but in a universe where the average matter density creates a relatively balanced gravitational background in all directions, a region with far less matter than average becomes a low point in the gravitational landscape. Matter around it tends to flow away from it and toward denser regions. From our point of view, that escape from the void looks just like a pushing force. The Milky Way is moving away from the dipole repeller. The result confirmed by Hoffman's team was very clear. The push from this void contributes to our total velocity almost as much as the pull from the Shapley Supercluster. For many decades, we had measured our cosmic motion and assumed that almost all of it came from matter pulling us along. This research showed that this picture was only half right. A significant part of our velocity of about 600 kilometers per second does not come from attraction, but from the absence of matter, from emptiness. This result was published in Nature Astronomy in 2017, and from that point on, anyone who wanted to understand the Milky Way's journey through the universe could no longer think only about heavy things pulling us along. They also had to account for the enormous voids that silently shape our path through their very emptiness. This is no longer merely an intriguing hypothesis to retell in science programs, but part of a cosmic picture confirmed by observation, and it forces us to change our familiar way of thinking about gravity. Throughout most of the history of science, when speaking about gravity, humans have almost always thought about what is present mass, density, dense regions of matter, large galaxy clusters, heavy superstructures pulling everything toward them. But the universe is not a uniform space. There are places where matter is concentrated far above the average, and there are also places that are almost unbelievably emptier than average. It is precisely the difference between those two sides, between the full and the empty, between dense regions and deficient regions, that truly governs the trajectories of galaxies on scales of billions of light years. In other words, the Milky Way is not only falling towards Shapley, we are also moving away from the void behind us. Nearly half of our galaxy's cosmic velocity, nearly half of the speed at which the Milky Way is drifting through its large-scale environment, may be explained not by some gigantic object or spectacular galaxy cluster, but by a region where there is almost nothing at all. No active pushing force is required. That void does not need to do anything except exist. When matter elsewhere creates a higher gravitational potential, everything naturally flows toward it. The region of space left behind becomes a zone of gravitational deficit, and from our point of view, it acts like a silent, continuous pushing force, with no luminous source we can point to on a sky map. This understanding has changed the way cosmologists model our motion through the universe. It has forced every calculation of the forces determining where we are going to be rewritten, and at the same time, it opened up a new question, one that had almost never been asked so directly before. If such a large void, so far away, can still make a significant contribution to our speed, then what else have we still not taken into account? The answer appeared much faster than people expected, and this time it did not come from emptiness. It came from a place hidden behind a curtain so thick that throughout almost the entire history of modern astronomy, what lay behind it remained nearly a blank area on the map. That curtain is the zone of avoidance, a completely real region, not a metaphor. Our Milky Way stretches across the sky as a dense, bright band of stars, gas, and dust. When telescopes try to look through that band, dust in the galaxy absorbs and scatters light, causing most of what lies behind it to nearly disappear from optical view. In other words, a significant part of the universe behind the plane of our own galaxy has been hidden from human eyes since modern astronomy began. Astronomers have long known this was a problem. They tried to work around it using infrared, then radio, because those wavelengths pass through dust better than visible light. By the early 2000s, many people believed the large-scale picture was nearly complete. There might still be a few small details yet to be discovered, but very few people thought that behind that wall of dust there could still be a structure on the scale of Shapley. Then that very assumption was broken. In 2016 and 2017, astronomer Renee Kraan-Korteweg at the University of Cape Town and her colleagues decided that the remaining gaps in this region could no longer be ignored. Using the AA Omega multi-fiber spectrograph and the Southern African Large Telescope, her team collected about 500 new redshift measurements from galaxies lying in the zone of avoidance, meaning 500 completely new data points from a region that many earlier surveys had treated as nearly empty. And the result made the entire field stop and take another look. Behind that dust band was a genuine galaxy supercluster, with a size and mass comparable to the Shapley Supercluster, located at a distance of around 800 million light-years and stretching somewhere between 320 and 400 million light-years across. It had been there all along, hidden behind the dusty disk of our own galaxy, and almost no one knew it existed. This structure was named the Vela Supercluster, after the constellation Vela in the southern sky. Part of it is obscured by the galactic plane, while the rest lies scattered through regions that older surveys had never examined deeply enough to recognize the full structure. This was not a small cluster or a minor detail that could easily be overlooked. It is one of the largest concentrations of galaxies in our nearby universe, comparable to what we have long considered the most prominent gravitational structures close to us. This discovery was published in 2017 Inches, the monthly notices of the Royal Astronomical Society, and because of its large mass, Vela almost certainly exerts a gravitational influence on the motion of surrounding galaxies, possibly including the Milky Way. The exact degree to which it contributes to our velocity is still under study, but initial estimates suggest that it could add several tens of kilometers per second, a number large enough that it cannot be ignored in any model of the local group's motion. This is far more important than it appears at first glance. For many decades, we have been building maps of the large-scale gravitational forces around us, and then using those maps to calculate where the Milky Way is going, how fast it is moving, and why. But all of those models were built without taking Vela into account. In other words, the map, once considered fairly complete, was actually still missing a major structure. Those models were not entirely wrong, but they were clearly incomplete. And what should make us pause is this: Vela may not be the final surprise hidden within the zone of avoidance. It may not even be the biggest surprise. After the discovery of Vela, the obvious question arose: what else lies behind that curtain? The zone of avoidance covers about 20% of the sky, meaning that from the perspective of the celestial sphere, nearly 1/5 of the observable universe had long been dimmed by our own galaxy. For many years, infrared had looked through it, and radio had done the same. And before the 2010s, the general consensus was that if anything still remained hidden, it was probably only small details. Vela proved that assumption was too confident. From 2017 onward, a network of radio telescopes in South Africa called Meerkat began carrying out blind surveys at the 21 centimeters wavelength of neutral hydrogen through the zone of avoidance. Meerkat consists of 64 radio dishes spread across the Karoo Desert, working together as an extremely sensitive instrument. At the 21 centimeters wavelength, radio radiation can pass through dust in the galactic plane with almost no absorption. In other words, The telescope does not need to find a way around that wall. It looks straight through it, and what it has seen just keeps appearing. In its first years of operation alone, hundreds of previously unknown galaxies were recorded. Not just isolated galaxies, but also groups, filaments, and signs that behind the galactic plane there may exist even larger architectures still waiting to be mapped. Those surveys are still ongoing. Each new data release continues to lengthen the list rather than close it. What makes this truly unsettling for cosmological models is the fact that the zone of avoidance should no longer be expected to contain surprises of that scale. Before this, astronomy had already had decades of infrared and radio observations to correct the models. And yet, in 2017, a supercluster comparable in scale to Shapley could still emerge almost out of the darkness. And Meerkat is suggesting that Vela may not be alone. Of course, serious science does not rush to declare more than the data allow. The structures that Meerkat is gradually revealing behind the galactic plane have still not been fully mapped. The resolution, coverage, and volume of data are still increasing. Researchers in this field regard most conclusions about new structures as provisional, but the direction of the discoveries is almost impossible to mistake each time we look deeper behind the wall. We see more than before. That alone should make anyone who thinks they are close to fully understanding the Milky Way's cosmic motion feel uneasy, because every new mass found beyond the zone of avoidance is a mass that we had not previously included in the gravitational model. It could be matter pulling us, deflecting our path, contributing to the velocity we once thought we mostly understood. We have mapped the easily observable part of the sky fairly well, but the rest, that nearly 20%, is still continuing to reveal its secrets even in recent years. And yet, the zone of avoidance is still not the most disturbing blind spot in the entire story. That title belongs to a signal that the scientific community still has not completely agreed on whether it is real or not. In 2008, NASA astrophysicist Alexander Kashlinsky published a paper that made the scientific community uncomfortable in the most literal sense. He did not claim to have found another galaxy supercluster, nor did he discover a new void. What he and his team believed they had seen was far bolder: a common drift, a synchronized motion shared by thousands of galaxy clusters across distances of billions of light years, all moving in the same broad direction. He called this phenomenon dark flow. The claim was very specific. Based on data from NASA's WMAP satellite, Kashlinsky's team measured an effect called the kinematic Sunyaev-Zeledovich effect. When photons from the cosmic microwave background pass through the hot gas in a galaxy cluster, they can experience a very small shift in energy due to interactions with moving electrons. The size of that shift depends on the velocity and direction of the cluster's motion. By measuring this signal across hundreds and then thousands of clusters, the research team constructed a velocity map on a very large scale. What they saw was not a mess of random motions. Thousands of galaxy clusters across a vast region of the sky appeared to share a coherent drift, with velocities somewhere in the range of 600 to 1.0 km per second, in the same general direction. This was no longer a local effect caused by a few nearby structures. If that signal is real, it extends across distances of several billion light-years. And if that is true, its implications would shake the entire framework of standard cosmology. Standard models predict that on sufficiently large scales, the motions of galaxy clusters should be nearly random, because on those scales the universe should look the same in every direction. Such a strong, synchronized bulk motion across such enormous scales is not something the standard model expects. Kashlinsky's interpretation was therefore extremely direct. The signal might indicate gravitational influence from structures lying beyond the observable universe, beyond our cosmic horizon, things we can never directly see. Structures large enough to pull thousands of galaxy clusters in the same direction through the part of space we can still observe. That idea alone was enough to make the scientific community react cautiously. And in fact, that is exactly how they reacted. Most researchers did not welcome this claim enthusiastically. The method was questioned. The statistical treatment was closely scrutinized. The strength of the effect was considered too large. Many scientists argued that other explanations, from foreground noise to biases in the WMAP data to subtle systematic errors in the signal processing pipeline, sounded far more plausible than the possibility of a gravitational influence coming from beyond the observable horizon. But what was troubling was that the data did not disappear easily. Koszaliński and his colleagues continued refining their analysis in the years that followed. They expanded the study to include more clusters, published follow-up papers in 2010 and 2012, and continued defending the view that some form of synchronized motion on extremely large scales might really exist. And at this point, the atmosphere of the story shifted again from the idea that we are pulled by superclusters, pushed by voids, obscured by the dust of our own galaxy, to the far more unsettling possibility that some part of our motion may also be influenced by what lies beyond the very portion of the universe we can observe. Although the original signal was controversial, one noteworthy point is that the result observed by Koszaliński and his colleagues did not fade away over time. Each time they reanalyzed the data, the direction of the motion remained the same, and the amplitude of the effect stayed within the same range. The debate, therefore, did not end with better arguments, but was merely put on hold while waiting for more precise data, and that data was already in orbit. In 2009, the European Space Agency launched the Planck satellite with the specific goal of mapping the cosmic microwave background with greater precision than any previous instrument. Planck had higher resolution, greater sensitivity, and more frequency channels to separate genuine cosmic signals from foreground noise, such as galactic dust or radiation from nearby sources. In other words, Planck had all the tools needed either to confirm the existence of dark flow or to bury it completely. Over 4 years of operation, the satellite measured the cosmic microwave background with unprecedented precision. In some frequency channels, it was up to 30 times more sensitive than WMAP, and instead of having only 5 frequency bands like WMAP, Planck observed in 9 different bands. When its first results were published in 2013, the cosmic map it provided was detailed enough to change many areas of cosmology. One of the questions Planck was expected to settle was precisely the dark flow issue. The Planck analysis team published their findings in several papers from 2013 to 2016. Their conclusion was fairly direct. They found no statistically significant evidence for dark flow. The upper limits they placed on any large-scale bulk motion were far lower than the 600 to 1. 0 kilometers per second reported by Koszaliński. Thanks to its wider frequency coverage, Planck could also separate foreground contaminants more effectively, especially dust and galactic radiation factors that many researchers had long suspected were responsible for contaminating the WMAP data. As a result, most of the scientific community regarded Planck's findings as an almost definitive verdict. Dark flow was most likely only a spurious effect, a methodological bias, or a noise signal that had been misinterpreted. However, Koszaliński did not accept that conclusion. He argued that the two analyses were not completely equivalent, that the galaxy cluster samples used were different, and that the Planck team's data processing methods also had their own limitations. In his view, the signal in the WMAP data could still be real, and the fact that Planck did not reproduce it was not necessarily a total refutation, but merely a different measurement on a different dataset. This debate was never fully resolved by either side yielding. It gradually faded beneath the weight of scientific consensus. And in cosmology, history has repeatedly shown that consensus can sometimes be revised when new data appears. What is important to note is that Planck's result was in fact a partial rebuttal, not an absolute negation. It did not prove that Koszaliński's data was wrong. It only provided a more precise measurement that did not detect a similar signal. The scientific community regarded that as a reasonable rejection. But as in many cases in science, conclusions that seem certain are sometimes reconsidered when new data emerges. At present, the prevailing view in cosmology is that dark flow has not been confirmed and is not included in the standard models of the large-scale structure of the universe. But Koszaliński continues to research and analyze it. Interestingly, while the debate over dark flow seemed to quiet down, measurements of galactic bulk motion from entirely different surveys, using completely different methods, have at times produced results that look very similar to what he once proposed. A question that seemed to have been closed opened again when, in 2023, an enormous survey of nearly 56,000 galaxies published results that brought the issue of anomalous bulk motion back to the center of attention. That survey was Cosmic Flows 4, the newest version of the galaxy velocity mapping project that Brent Tooley and his collaborators had built over many years. Unlike projects that were controversial from the beginning, Cosmic Flows is a very cautious research program, focused on collecting precise galaxy distance measurements in order to determine their peculiar velocities relative to the general expansion of the universe. The fourth version of the catalogue, published in 2023, included 877 galaxy distance measurements, the largest dataset ever assembled for this purpose. The goal of the project is fairly simple. In principle, measure the velocities of galaxies at different distances, compare them with what the standard cosmological model predicts, and then test whether the two pictures match or not. But this time, the picture did not fully cooperate. On scales of about 150 to 200 megaparsecs, equivalent to 500 to 650 million light-years, the Cosmic Flows 4 data showed that galaxies are participating in large bulk flows, meaning regions where many galaxies are drifting through space in a common direction far beyond what cosmic expansion alone can explain. The velocity of these flows was measured at about 380 to 430 kilometers per second. Meanwhile, the standard cosmological model lambda CDM, the foundation of most modern cosmological theory, predicts that on those scales, collective flows should be only about 140 kilometers per second. The difference is not small. In some cases, the measured velocity is 3 times greater than the prediction. The probability that the Cosmic Flows 4 data would appear within the framework of the standard model is estimated to be only about 1 inch, 650 ling in the statistical language of physics. That corresponds to a significance level of 3 to 6 sigma, a signal strong enough to force the scientific community to pay attention. Of course, the debate is still not over. The Cosmic Flows team itself, led by Brent Tooley, also acknowledges that this is an anomaly that needs further testing. One possibility is that systematic errors exist in the distance measurements, because measuring galaxy distances with high precision is one of the most difficult tasks in astronomy. Even a small deviation can accumulate into a large signal when the data extend across hundreds of millions of light-years. But there are also researchers who argue that the velocity field on this scale is genuinely anomalous and reflects physical factors that the standard model does not yet fully describe. So far, there is no clear consensus. What makes this result especially noteworthy is that it does not come from a new and untested technique. Cosmic Flows is a long-running project, with methods that have been used and tested through multiple earlier versions. And even more noteworthy is that as the amount of data increases, the anomalous signal does not weaken but instead grows stronger. Normally, if an effect is only statistical noise, it gradually disappears as more measurements are added. But when a real signal exists, it often remains stable or even becomes clearer with a larger data sample. If the bulk motion measured by Cosmic Flows 4 is real, then it means that the universe around us contains collective motions much larger than those predicted by the standard model. That could imply that the distribution of matter around us is more complex than what we have mapped, or that there are large-scale physical processes we do not yet fully understand. And Cosmic Flows 4 is not the only measurement that has led scientists to think in that direction. At the center of every discussion about our cosmic motion lies a familiar number, 630 kilometers per second. That is the velocity of the Milky Way relative to the reference frame of the cosmic microwave background radiation, the oldest light still existing from the time shortly after the Big Bang. We measure this velocity through the CMB dipole. The background radiation is slightly warmer on one side of the sky and slightly colder on the opposite side. This small difference appears because the Milky Way is moving toward the warmer region. The degree of the temperature difference tells us the speed, and its direction tells us where we are going. The measurement shows that our galaxy is moving at about 630 kilometers per second toward the Hydra Centaurus constellation. This is one of the most precise and reliable measurements in all of cosmology. However, when scientists measure our motion in another way by looking at the distribution of radio galaxies, quasars, and distant radio sources, they get a somewhat different result. Because we are moving, in theory, there should be slightly more astronomical sources in the direction we are heading, and slightly fewer behind us, due to the Doppler effect and the aberration of light. This effect is called the radio dipole, or matter dipole. According to the standard model, its direction and magnitude should match the CMB dipole. But in reality, that is not entirely the case. Multiple independent surveys of radio galaxies and quasars show that the matter dipole is nearly twice as large as the value inferred from the CMB. Its direction is also only approximately similar. Not perfectly aligned, the level of discrepancy lies in the range of 3 to 5 sigma, depending on the survey and the method of analysis. It has been detected in NVSS data, in the Catwise Quasar Catalogue, and in many other studies published from 2020 to 2023. At the 3 to 5 sigma level, this signal is no longer just a whisper in the data. It is more like a reminder that there may still be something in our cosmic motion that we do not fully understand. One proposed possibility is that the CMB dipole is not entirely caused by our motion, but may contain another component that has not yet been fully explained. And if that is true, the story of where the Milky Way is going in the universe may be even more complicated than we think. One possibility that has been raised is that part of the temperature asymmetry in the cosmic microwave background is not due to our motion, but may originate from the initial structure of the universe itself. If that is true, then the CMB dipole, the thing we use to measure the Milky Way's velocity of 630 kilometers per second, does not fully reflect our true motion. Another hypothesis is even bolder. Perhaps the universe is not completely isotropic on the largest scales, meaning that the distribution of matter is actually different in different directions, even at distances where we normally expect everything to become uniform. If this is true, it would challenge one of the foundations of modern cosmology, the cosmological principle, the assumption that the universe looks the same in every direction when viewed on a sufficiently large scale. Both possibilities are serious, and at present, neither has been definitively resolved. Two measurements aimed at the same physical phenomenon, our motion through the universe, are producing clearly different results. One result is nearly twice as large as the other. Both were carefully constructed. Both were published in peer-reviewed scientific journals, and so far there is still no broadly accepted explanation for this disagreement. To understand why those questions matter, we need to look more deeply into the fundamental structure of the universe. The positions of galaxies are only part of the story. What matters more is the invisible structural framework beneath them. Cosmologists call that structure the cosmic web, and the name describes it quite accurately. On the largest scales we can observe, the universe is not a space where galaxies are randomly distributed in all directions. Instead, they are arranged into enormous filaments of matter, stretching across hundreds of millions of light years. These filaments intersect at points called nodes, where many streams of matter converge and form galaxy clusters or superclusters. Between those filaments are enormous voids, regions where matter has been almost completely drained away. When scientists simulate this structure on computers, the result looks like a gigantic three-dimensional network, where each filament connects to many others, and each node is a region of extremely high matter concentration. Within that network, the Shapley Supercluster is one of the largest nodes in our nearby universe, a place where many filaments of matter converge and accumulate into an enormous mass. The dipole repeller, by contrast, is a void, an empty region where matter is sparse and gravity causes everything to drift away from it in all directions. Laniakea is a basin of attraction, a region where galaxy velocities, after subtracting the expansion of the universe, all flow toward the same low point in the gravitational landscape. The shape of the supercluster in which we live is therefore defined by the flow of matter through this cosmic web, and that structure did not appear randomly. It originated from tiny quantum fluctuations in the early universe. Those fluctuations created regions that were slightly denser than others in the matter distribution. Over the billions of years that followed, gravity amplified them. Matter fell into the denser regions, forming filaments. The intersections of filaments became galaxy clusters. The regions in between were gradually drained out and became voids. What is remarkable is that most of the matter involved in this process cannot be seen. Dark matter makes up about 80–85% of the total amount of matter in galaxy clusters. It does not emit light, does not interact with light, and we know it exists only through its gravitational influence on ordinary matter. In the cosmic web, dark matter is the true skeleton. The filaments, the nodes, the entire architecture of the network are made primarily from it. Ordinary matter, the kind that forms stars, gas, planets, and us, only falls into the gravitational wells that dark matter created first. This leads to a rather strange truth: we are being pulled and pushed by things we cannot see, towards structures we cannot fully observe, within a network built mostly from a type of matter we have never directly detected. The Shapley Supercluster pulling us is made largely of dark matter. The dipole repeller, the void pushing us, is defined by the absence of that invisible kind of matter. The Vela Supercluster behind the galactic plane is also a region of concentrated dark matter, in which galaxies merely trace the outline. And Laniakea, the basin of attraction in which the Milky Way lies, is also a structure carved into space by matter that we cannot directly see. In other words, every force guiding the Milky Way's journey through the universe is governed by components that do not appear on any map of light in the sky. And that is not a small detail. It is the central truth of our cosmic motion. We are moving through a universe of which we can see only part, guided by forces we can only infer, and heading towards structures that we are still in the process of discovering. Even our cosmic address has changed many times as human understanding has expanded. For most of human history, Earth was considered the center of everything. Then we realized it was only a planet orbiting a star. Then that star was only one of hundreds of billions of stars in the Milky Way. Then the Milky Way became one galaxy within the local group. Then the local group was placed inside the Virgo Supercluster, a structure about 110 million light-years wide. For most of the 20th century, Virgo was considered the answer to the question, where do we live in the universe? But in 2014, Brent Tully's research redrew that boundary. By using galaxy flow data rather than simple distance alone, the research team defined superclusters according to true gravitational basins. By that definition, Virgo is not our home. It is only a small branch within a much larger structure, Laniakea, about 520 million light-years across, containing about 100,000 galaxies and having a mass close to 10 to the power of 17 times the mass of the Sun. Laniakea is nearly 5 times larger than the Virgo supercluster. It became our new cosmic address, but that address did not remain fixed for long either. A study published in 2024 re-examined the relationship between Laniakea and the Shapley Supercluster, which lies about 650 million light-years from us. Previously, Shapley had been considered a separate structure, a gigantic neighbor pulling us from the outside. But the new analysis suggests there is about a 60% chance that Laniakea is actually only a sub-basin of Shapley, like a branch of a river flowing into a larger system. If this is confirmed, then Shapley is not merely a distant attractor, it may actually be the larger structure we live inside. If so, our cosmic address will have to change once again. And when we look back over this whole history, a clear trend appears. Every decade, the cosmic map is redrawn. With each revision, Earth becomes a smaller part of a larger structure, not because humans enjoy making things more complicated, but because every new tool allows us to see farther. Every new survey discovers more structure, and almost every structure we have ever mapped turns out to be only part of something larger that we had not yet measured. And then there is a structure at the farthest edge of anything any survey has ever touched. A structure that, if it truly exists, would place this entire story in a completely different context. everything we have just discussed, Shapley. The dipole repeller, Vela, Laniakea lies within a range of a few 100 million to a few billion light-years around us. Meanwhile, the observable universe extends nearly 46 billion light-years in every direction. According to the standard cosmological model, on scales larger than about 2 billion light-years, all structure should gradually smooth out. Small irregularities should be averaged away. This is precisely a consequence of the cosmological principle. But in 2013, a research team led by Attila Horvath, while analyzing the distribution of gamma-ray bursts, the most energetic explosions in the universe found a notable concentration associated with the constellations Hercules and Corona Borealis. This structure was named the Hercules-Corona Borealis Great Wall. Its estimated size is about 10 billion light-years, nearly 10% of the diameter of the entire observable universe. If that number is correct, it would be the largest structure ever known, and according to current theories, it should not exist. Of course, this discovery is still controversial. Mapping gamma-ray bursts is not as direct as measuring galaxy redshifts, and the data can be affected by many observational factors. So the scientific community does not yet regard this Great Wall as a confirmed reality in the same way as Shapley or Laniakea, but it is still considered a serious candidate, and the possibility of its existence alone is enough to make cosmologists think again. If we look back at the entire picture, everything seems to converge on one common point. Earth orbits the Sun. The Sun lies within the Milky Way. The Milky Way lies within Laniakea, which may in turn lie within Shapley. Shapley is a node in the cosmic web, built primarily from dark matter. The dipole repeller pushes us from behind, while Shapley pulls us from ahead. The zone of avoidance still hides unknown structures. The CMB dipole and the matter dipole do not perfectly match. Cosmic flows foreshows galaxy flows 3 times larger than predicted by the standard model. And on the largest scales, there may exist structures spanning billions of light-years that current theory cannot explain. For 25 years, the standard cosmological model, lambda cold dark matter, LCDM, has been the foundation of almost all our understanding of the universe, how galaxies form, how matter clumps together, how large structures grow from the tiny fluctuations of the early universe. It has been tested by countless data sets and was called the consensus model because so many observations led to the same picture. But consensus does not mean perfection, and recently, the cracks have begun to become difficult to ignore. Cosmic flows foreshows galaxy flows up to 3 times larger than predicted. The CMB dipole and the matter dipole do not match. The Hercules-Corona Borealis structure, if real, would far exceed the size limit allowed by LCDM. And the story of dark flow has still not completely disappeared from discussion. Each individual anomaly could be explained by measurement error, statistical bias, or observational limitations. But when many anomalies appear together within the same theoretical framework, scientists begin to ask a larger question: is the picture we are using to describe the universe still complete? The scientific community has very good reason to be cautious in the face of any anomaly. A strange result, by itself, is still only a strange result. But when multiple independent anomalies appear together and all point toward a similar possibility that the universe on the largest scales may be less smooth, less uniform, and harder to describe with the lambda CDM model than we once thought, then the situation is completely different. In recent years, some cosmologists have begun to say openly what used to be whispered only in conference hallways: the standard model may not be wrong, but it may be incomplete. There may be physical effects on the largest scales that the current framework does not yet fully encompass. And that relates directly to this entire story. Because the Milky Way's motion of about 600 kilometers per second towards something we still cannot fully see ought to be explainable by lambda CDM, by the Great Attractor, by Shapley, by known structures, by known physics, by known mathematics. But if that framework is beginning to show cracks at the edges, then the origins of this motion may still not be fully understood. The pull that is guiding us may not yet have been completely accounted for, and that unexplained remainder may require more than what the cosmological model that dominated for an entire generation once allowed. In the past, that possibility would have been almost unthinkable. Now, it has become the subject of papers, conferences, and even research careers lasting decades. The year 1998 was a major turning point. At that time, two independent research teams were measuring the brightness of very distant supernovae, specifically Type IR supernovae stellar explosions whose peak brightness is so uniform that they can be used as standard candles to measure cosmic distances. By comparing their observed brightness with their true brightness, astronomers could infer whether the universe had been expanding faster or slower at different stages in the past. Both teams expected the same thing: the expansion rate of the universe should be slowing down, because gravity was assumed to be doing its familiar job, pulling matter together and gradually slowing the outward motion from the Big Bang. But what they saw was the exact opposite. The expansion of the universe was accelerating. Space was not only continuing to expand, but was expanding faster and faster. Something was overcoming gravity on the largest scales, pushing space itself apart. This discovery later led to the Nobel Prize in Physics in 2011, and the phenomenon itself is no longer disputed. The acceleration is real. The name given to whatever causes it is dark energy. That name does not mean we actually understand what it is. It does not shine, does not radiate heat, and cannot be directly detected. It is mainly a mathematical label for an observed effect. According to the best measurements we have today, dark energy accounts for about 68% of the total energy density of the universe. Ordinary matter, everything you can see, touch, weigh, and measure, accounts for only about 5%. Dark matter makes up about 27%, and the largest part, about 68%, belongs to something whose true nature we still do not really know. That changes our story in a profound way. The Milky Way is falling toward the Great Attractor, a region of concentrated matter about 150 million light-years away. Farther still, Shapley continues to pull from about 650 million light-years away. That motion is real. It has been measured. It is not an illusion, but at the same time, the space between us and those structures is also expanding. And because of dark energy, that rate of expansion is not remaining constant but is increasing. In the expanding coordinate system of the universe, the Great Attractor and Shapley are in fact also moving away from us. Even as we are falling toward them, this creates a very strange image. The Milky Way is chasing a destination that, in a deeper physical sense, is also running away. At the current scale, gravity is still strong enough to give us a peculiar velocity, a motion above and beyond simple expansion. But at greater distances and over longer timescales, the acceleration caused by dark energy will ultimately win. Dark energy acts uniformly across all space, without negotiating with the local pulls of individual superclusters. The mathematical consequence of this is very clear. We will never reach the Great Attractor. We will also never reach Shapley. The free fall continues. But the distance to the target always expands faster than our ability to close it. This is not a metaphor, but a direct consequence of the equations describing the measured expansion. We are in a permanent fall toward a horizon that the universe itself guarantees we can never cross. In 2014, when Brent Tully's team used peculiar velocity data from more than 8,000 galaxies in cosmic flows 2 to map the gravitational basins of the nearby universe, they discovered a vast structure in which the Milky Way, the Virgo cluster, the Great Attractor region, and thousands of other galaxies all flow toward a common system. They named it Laniakea, immense, boundless heaven. At first glance, a structure about 500 million light-years across and containing the mass equivalent of 100 quadrillion stars seems like something very stable, almost eternal. But in fact, it is not a tightly bound gravitational system. This is a point often overlooked in popular retellings, but it is extremely important. A truly gravitationally bound system such as the Milky Way itself, or the local group, will continue to stay together despite the expansion of the universe. But Laniakea is not that kind of structure. It is a flow pattern, a way of describing where galaxies are currently heading, not a unified block that will endure forever. Over tens of billions of years, dark energy will gradually tear it apart. In the outer regions, accelerating expansion will eventually overcome the weak gravitational gradient pulling matter inward. The current flow will slow down, and at the farthest edges, it may even reverse. What now looks like a coherent basin will ultimately break apart into isolated islands of local systems that still remain gravitationally bound. The Great Attractor region itself will also not remain intact as it is now. The galaxy clusters within it are moving, merging, and changing over sufficiently long timescales. The structure we are falling toward will change shape, fragment, and lose its familiar form. Compared with that, there is a nearer and much more certain fate in about 4 to 5 billion years. The Milky Way and Andromeda will collide. That is almost already determined, because it is a local system sufficiently bound that dark energy cannot prevent it. But the fall toward the Great Attractor is entirely different. Local bound systems will survive. Large-scale flow patterns will not. In that sense, Laniakea has an expiration date written into the physics of the universe. We are drifting in a river that will itself eventually run dry, even though at the moment it is still carrying us along. This leads to a question that seems simple but is actually one of the hardest problems in observational cosmology. How far out do we need to look to fully explain the motion of the Milky Way? The technical concept here is convergence depth, the distance at which, if you include all the mass inside it, the gravitational numbers close. The observed peculiar velocity is fully explained, and you no longer need to look farther. In the early 1990s, the first models suggested that convergence would appear at around 100 to 150 million light-years. That meant the Great Attractor region and its surroundings should be enough. But then better data appeared, progressively deeper surveys, from PSC to 2-mass and then to cosmic flows, continuously pushed the convergence depth farther out. Shapley, about 650 million light-years away, turned out not to have only a small influence, but to contribute significantly to our velocity. In the main analysis of Cosmic Flows 4, the estimated convergence depth had already exceeded 300 million light-years. But even then, Shapley's contribution had still not vanished. That means after hundreds of millions of light-years of observation, the numbers still have not completely closed. Every time the reach of measurement increases, the origin of our motion seems to retreat a little farther away. There are two ways to read this trend. The first is more optimistic, perhaps convergence is real, but simply lies farther out than we once thought. Once surveys go deep enough, all the relevant mass will be included, the equations will close, and the Milky Way's motion will be completely explained by structures within the observable region. In this interpretation, the problem lies in the depth of the measurements, not in the physics itself. But there is another, more troubling interpretation. Perhaps the convergence depth keeps receding because part of the gravitational origin of this motion lies beyond every depth we can ever reach. The zone of avoidance still hides a significant part of the sky behind the dusty disk of our galaxy. The deeper universe still contains structures that have not yet been catalogued, and at the ultimate limit, there is the cosmic horizon, the boundary of the part of the universe from which light can reach us. If mass beyond that boundary is contributing to our motion, then convergence may never be found. Not because our technology is insufficient, but because the universe itself does not allow us to observe past that point. Some researchers have noted that the way bulk flow measurements behave their persistent existence at ever greater depths, together with their nearly consistent direction, is the kind of behavior one would expect if the source of influence lay beyond observation. This does not confirm dark flow, but it tells us something honest about the limits of any model based only on what we can see. The mass budget explaining the Milky Way's motion may not be entirely local, may not be entirely visible, and the final accounting of this problem may require us to look towards something that no telescope will ever reach. It is in that context that dark flow returns like a shadow that refuses to fully disappear. In 2008, Alexander Kashlinsky published the signal he gave that name. The claim was very specific by combining galaxy cluster data with the cosmic microwave background. His team found a synchronized motion of galaxy clusters across a volume of space too large to be explained by known gravitational sources, hundreds of millions of light years, perhaps even more than that, all drifting in one direction. The scientific community was skeptical from the beginning, and that is entirely understandable. The signal was very faint. The technical method was highly sophisticated. Its implications were enormous. By 2013, the Planck satellite published its own analysis and found no statistically significant dark flow signal. Many researchers considered that the end of the matter, but Koszaliński did not accept it, and his response was not an emotional objection, but an argument about method, that the galaxy cluster samples were different. The signal extraction techniques were different, and that Planck's failure to see the signal did not mean WMAP was certainly wrong. The scientific community generally still leans toward Planck, but the question itself has never fully died. And as other anomalies from the bulk flow seen in cosmic flows, to the mismatch between the CMB dipole and the matter dipole continue to appear. Dark flow no longer stands alone as an idea too strange to take seriously. It begins to fit into a broader picture, in which many independent signals all suggest the same uncomfortable feeling, perhaps on the largest scales. The universe is not as simple as our model once promised. If we look back at the whole story, what makes it memorable is not just a single discovery, but the way all the pieces stack on top of one another. The Milky Way is moving through the oldest radiation in the universe at about 630 kilometers per second. We know that direction. We know it is not random. We know that part of the force comes from the Great Attractor, part from Shapley, part from voids like the dipole repeller, and perhaps more from Vela and other structures that are still emerging from behind the dust of the galaxy. We also know that the large structure we currently inhabit, Laniakea, may not be our final address, and that it too will eventually dissolve under the influence of dark energy. We know that the standard model still works very well in many places, but is beginning to struggle in the farthest, largest, and faintest ones. We know that there are signals that still cannot be reconciled with one another. And above all, we know one truth that is both beautiful and sad. We are moving towards something we may never reach. Through a universe whose structure is woven largely from matter we cannot directly see, while the space between everything continues to expand and pull all shores farther apart. Perhaps that is the strangest part of the whole story. Not merely that Earth is rushing onward in silence, but that we are drifting inside an unfinished map, guided by forces not yet fully understood, heading toward a destination that keeps receding, in a universe that every time humanity thinks it is close to fully understanding, opens yet another layer deeper, larger, and more mysterious than before. Koszaliński's team did not step back afterward. In subsequent papers, he and his collaborator Fernando Atrio Barandella argued in great detail that the Planck team had applied incorrectly, or at least applied in a fundamentally different way, the kinematic Sunyaev-Zeldovich technique, which is the very tool at the center of the entire dark flow measurement. According to them, the different ways of filtering the data and assigning weights to the galaxy clusters meant that the two teams were not actually testing the same hypothesis in the same way. Koszaliński argued that Planck and WMAP had been placed side by side as if they were answering the same question with the same test, when in reality they were processing the signal along different paths. He continued publishing new analyses. In later studies, Koszaliński and Atrio Barandella argued that if their original method were correctly applied to the Planck data itself, a statistically significant dipole signal would still remain. In other words, the signal did not disappear when a more sensitive telescope appeared. It changed depending on how humans processed the data from that telescope. This is not a comfortable situation for science, because both sides are serious. Both use real data. Both have clear methods, yet they arrive at different conclusions. And to this day, neither side has identified a specific, decisive flaw in the other's work sufficient to close the debate. Koszaliński is currently pursuing a new line of testing through an instrument called NIRBDE, the Near-Infrared Background Dipole Experiment, designed for the European Space Agency's Euclid satellite. Launched in 2023, The goal of this project is to test the dark flow hypothesis through an entirely different signal channel, no longer relying on microwave data from the hot gas in galaxy clusters, but instead on the near-infrared background, a different kind of signal, a different method, but still aimed at the same old question: is there, or is there not, an anomalously large coherent motion beyond what the standard model allows? This instrument has not yet produced final results, but the very fact that it was built already shows something important about how science really works. Science is often retold like a tidy sequence question. Experiment. Answer. But dark flow does not follow such a clean path. It is a far more realistic image of science, a prolonged, tenser, unresolved debate between serious people and serious data sets. The scientific community has not confirmed dark flow, but neither has it proved it false in an absolute sense. What remains is an uncomfortable grey zone, the kind of grey zone that does not make for simple newspaper headlines, but is enough to keep cosmologists awake for many years. Kashlinsky has defended this view for nearly 2 decades. That persistence, if understood properly, is not noise. It is the way science either discovers something it once overlooked, or eventually succeeds in discarding a signal that cannot be confirmed. Either way, the new results in the coming years will truly move this story forward. And here, we come up against a wall deeper than any band of galactic dust, not a wall of matter, but a wall of time. Our observable universe extends about 46 billion light-years in every direction, but beyond that boundary, the universe may continue forever. It is just that no signal, no light, no information has had enough time to reach us in the 8 billion years since the Big Bang. What lies beyond that boundary is, by definition, impossible to observe directly. This is not a limit of technology. It is a limit imposed by physics itself. And if we return to dark flow, we can see why it makes so many people uneasy. If the signal Kashlinsky measured is real, and if it is not caused by noise or error, then the most direct explanation would involve gravitational influence from structures lying beyond the observable horizon. Within the framework of cosmic inflation, the early universe went through a phase of extremely rapid expansion. So rapid that regions of space once close together could have been pushed beyond our ability to observe. In some models, the original quantum fluctuations may have seeded very large density regions just beyond the horizon, close enough to exert a gravitational influence on the edge of the universe that we can still see. This idea remains controversial. Many physicists argue that any influence from beyond the horizon is impossible to test by any method we can imagine. And some argue that it does not fit with the standard predictions of inflation. But the important point is this: it has not been ruled out mathematically. Inflationary cosmology itself allows physical possibilities beyond our field of view that models considering only the region inside the horizon do not necessarily have to take into account. What makes this idea truly staggering is not just its abstraction, but the scale it suggests. The structures we have already mapped are enough to exhaust the imagination. Shapley stretches across hundreds of millions of light-years. The Hercules, Corona Borealis Great Wall, if it is real, extends across billions of light-years. Those are still structures within the observable universe, in principle still traceable by telescope. But dark flow, if it exists, suggests something stranger still there. May exist structures even larger, perhaps much larger, lying beyond the boundary that we can never cross by observation. In that case, the Milky Way would not only be falling towards something it has not yet seen clearly, it could also be responding to something it will never be able to see directly, governed by a part of reality that physics allows to exist, but observation can never reach. And even if dark flow ultimately dissolves as a statistical illusion, the larger question remains: is there structure beyond the observable universe? Inflation almost says that there almost certainly is. Could some part of that structure be large enough and close enough to the horizon to influence what happens inside? That is still a genuine open question. We may never have a single observation sufficient to answer it definitively, but the question is not vague at all. It has a very clear mathematical form. and the next generation of surveys will at least tell us whether the signals inside the observable universe remain consistent with influence coming from outside. We are living in a universe of which we can see only a part. That statement is not poetic. It is the most honest description of our condition. In 2023, the Cosmic Flows 4 catalogue was published as the most complete compilation of peculiar velocities ever assembled, with more than 56,000 galaxy distance measurements and coverage extending to about 600 million light-years. When the research team performed a bulk flow analysis, meaning they measured the synchronized motion of galaxies within a large volume of the nearby universe, they obtained a value in the range of 380 to 430 kilometers per second. The direction of that motion agrees with earlier surveys, agrees with the flow toward the Shapley region, repeats across multiple different methods of analysis, and remains stable within the intrinsic error range of the catalogue itself. But under the lambda CDM model, bulk motion on such scales ought to be significantly smaller. The standard model expects a smoother universe, with less collective motion. The probability of obtaining such a large bulk flow purely by chance, in a universe fully obeying lambda CDM, has been estimated at about 1 inch 650,000 at certain angular scales. Pause for a moment on that number. 1 in 650,000. That is not the kind of number scientists dismiss easily. A result of 1 inch 1,000 could still be noise. A result approaching 1 inch, the hundreds of thousands or millions, begins to become the kind of signal that compels explanation. It is the kind of number that makes physicists recheck their entire analysis several times before daring to publish. And they did. But then in 2026, a reanalysis using Bayesian methods on the cosmic flows, 4 data appeared in the scientific literature. This study focused on one potential source of systematic error called survey anisotropy, that is, the survey not being uniform across the whole sky. Some regions were sampled more densely, others more sparsely, and that unevenness could itself create the impression of a bulk flow, even if it were really only a geometric effect of the sampling. When the new analysis team applied a correction for this factor, the bulk flow signal decreased significantly, down to about 75 to 80 kilometers per second in some interpretations of the corrected dataset. At first glance, this sounds like a solution, but it is not, because even the 75 to 80 kilometers per second level still leaves a certain amount of tension with the predictions of lambda CDM. That tension is smaller than before, easier than before, and perhaps manageable with more refined adjustments. But it does not disappear entirely. The anomaly shrinks, but it does not dissolve. And that is exactly the pattern most worth following in this whole story every time a bulk flow anomaly is reanalyzed, corrected, and then corrected again. Some residual always remains. It has never truly fallen exactly to the level the standard model expects. Each new analysis produces a somewhat different number, but no number has yet landed completely where lambda CDM wants it to be. Such behavior can be read in 2 ways. One is that this is the trace of a real signal, partly obscured by measurement challenges that are very difficult to handle. The other is that the residual is merely the combination of many small systematic errors that no one has yet managed to fix all at once. Both interpretations are currently defended by serious researchers, and both lead to the same honest conclusion. Cosmic Flows 4 has touched something that the standard model cannot explain comfortably. As of today, no analysis has made the issue disappear completely. That number is still there, patiently waiting for a better theory, a better correction method, or a deeper catalogue, either to put it in its proper place or to confirm that it really is a new sign. Because in the end, every measurement of the Milky Way's velocity is also a measurement of the universe itself. This deserves to be emphasized more than it usually is. When astronomers track the peculiar velocity of our galaxy, the part of its motion that cannot be explained by local expansion, the part that must come from gravity, they are not merely plotting a destination. They are reading the gravitational field of the universe on scales of hundreds of millions of light-years. They are reconstructing the distribution of mass from the motions that mass itself creates. Gravity does not reveal itself through light. No telescope can point directly at a gravitational field and photograph it. The only thing we can do is observe how matter responds to that field. In that sense, the velocity of the Milky Way is a record of every region of concentrated mass, important enough in the gravitational history of our galaxy. Its speed and direction encoded across cosmic time. The clearest expression of that is the CMB dipole. The cosmic microwave background reaches Earth with a very small asymmetry. One side of the sky is slightly warmer, the opposite side slightly cooler. This asymmetry reflects our motion relative to the rest frame of the background radiation. We are moving at approximately 600 kilometers per second toward a region of sky near Centaurus. That number has been confirmed. That direction has also been confirmed. Multiple independent measurements converge on it. And everything else in this entire story, the Great Attractor, Shapley, bulk flow anomalies. The convergence depth problem is fundamentally just an attempt to answer one single question: why does the CMB dipole have exactly that value? What mass, at what distance, creates a gravitational pull strong enough to push us at exactly that speed, in exactly that direction? If that motion is anomalous, then the structure creating it is also anomalous. That would mean matter in the universe may be clustering more strongly on the largest scales than lambda CDM allows. For that reason, peculiar velocity surveys today are no longer used only to hunt for attractors. They have become precision tests of the standard model itself. A velocity field consistent with the predictions of lambda CDM would reinforce confidence that the model is correctly describing the universe on large scales. But a velocity field that continuously departs from those predictions would be evidence that something is missing. Cosmic Flows 4 is exactly this kind of test. And before it, every other peculiar velocity catalog was as well. In the coming years, many ongoing surveys will push this question much farther. DESI, the Dark Energy Spectroscopic Instrument, is carrying out the largest survey ever of galaxy distribution and large-scale structure. The legacy survey of space and time at the Rubin Observatory will continue expanding that map. Euclid will provide different kinds of constraints through maps of galaxy shapes and weak gravitational lensing. In the view of many cosmologists working directly in this field, the next few years may become the most information-rich period in the history of this very question, not because one final revelation is guaranteed to appear, but because the density of the data will increase by orders of magnitude. The ongoing surveys will map the velocity field at a depth and density no previous generation could come close to. When those maps become more complete, one of two things will happen. Either the anomalies will gradually be explained away, the bulk flows will shrink closer to the predictions of lambda CDM, and the standard model will be confirmed with new precision, or they will become deeper, more persistent, and then the universe will reveal itself to be genuinely stranger than the current framework allows. One possibility confirms what we already believe. The other throws open a new door. Both are important, and what is striking is that we may know which side we are standing on sooner than many people think. The tools are already operating. DESI began its main survey in 2021 at Kitt Peak in Arizona. The question of where the Milky Way is being pulled, and by what, no longer lies in the realm of distant speculation. It is being measured, right now, by the most powerful instruments humanity has ever built to read the motion of the universe. In the next decade, this picture will enter its sharpest phase yet. When completed, DESI will measure the redshifts of about 40 million galaxies and quasars, spanning roughly 11 billion years of cosmic history. From those redshifts, scientists will not only reconstruct the expansion of space, but will also be able to separate out the peculiar velocities of galaxies, thereby mapping bulk flows at a depth and data density no previous survey has ever reached. If Cosmic Flows 4 exposed an uncomfortable problem for the standard model, then DESI will not merely continue that work but amplify it many times over. Where earlier catalogues could measure only thousands or tens of thousands of galaxy distances, DESI will work on the scale of millions. Where older surveys covered only parts of the sky, DESI is scanning a very large part of the sky with exceptionally high detail. The velocity field it produces will be the most complete three-dimensional map of gravitational motion humanity has ever built. At the same time, in Chile, the Vera C. Rubin Observatory is entering operation. Over 10 years, the legacy survey of space and time will repeatedly image the entire southern sky, accumulating a dataset so large that its volume is measured in petabytes. One of Rubin's most important goals is to discover hundreds of thousands of Type Ia supernovae, the very standard candles that helped humanity discover the acceleration of the universe in 1998. Each such supernova is a distance measurement. Each distance measurement then becomes an input for constructing the peculiar velocity field. That means places that previously had only a few hundred data points will, in the near future, have hundreds of thousands. In space, the European Space Agency's Euclid satellite, launched in 2023, has also begun operating. It is mapping the shapes and positions of billions of galaxies across about 10 billion years of cosmic history. The weak gravitational lensing maps produced by Euclid will show the large-scale structure of matter with a precision that ground-based surveys find very difficult to match. And at the same time, Euclid also opens the possibility of retesting the most controversial ideas, including dark flow, through completely different signal channels from those used before. On the other side of the observable sky, Meerkat in South Africa is still steadily working on the very region where astronomy has been blind for many decades, the zone of avoidance, the region hidden by the thick dust of the Milky Way's plain. This is an especially important area because behind it there may exist concentrations of matter directly related to the peculiar velocity of the Milky Way. Optical telescopes are almost helpless against that dust layer, but radio waves are not. Meerkat is gradually cataloguing the galaxies in this hidden region, slowly filling in the blank spaces that have existed for too long on our gravitational maps. And it is at this point that all the observational directions of this decade begin to converge. Over the next 10 years, data from DESI, Rubin, Euclid, and Meerkat will all touch the same question. The bulk flow anomaly detected by Cosmic Flows 4 will be tested with a catalogue many times larger. The tension between the CMB dipole and the matter dipole will have to face the most complete map of galaxy distribution humanity has ever had. The zone of avoidance will be significantly illuminated, and the problem of convergence depth, the distance required to fully close the gravitational budget, explaining our motion, will either close or remain open even when the data have become this complete. If it still remains open at that level of precision, then we will no longer be able to blame simple observational limits. At that point, it will be a real problem of physics. What matters is that this investigation is not slowing down at all. On the contrary, it is entering its sharpest moment. Surveys deeper than anything ever seen before are underway, while the anomalies are still present, silently waiting to be confirmed or explained. Today, we know more about the Milky Way's direction of motion than any generation before us. We know its speed, about 600 kilometers per second relative to the cosmic microwave background, a value confirmed through decades of observation and multiple independent methods. That number is almost certain not to change in any significant way. We know the direction of that motion, toward the region of sky near Centaurus, toward a concentration of mass about 150 million light-years away, and farther still toward Shapley at about 650 million light-years away. That direction has remained stable through more than 30 years of increasingly precise observations. We know the structure to which we belong, a gravitational basin hundreds of millions of light-years wide, in which our galaxy is sliding along invisible lines of force toward a center it will never reach. We know about the void behind us, the dipole repeller, a gigantic region of matter deficit that is pushing us forward just as surely as the superclusters in front of us are pulling us closer. We are being pulled forward and pushed away from behind at the same time. Both together write our trajectory. And we also know something rather cold: we will never arrive. Dark energy makes that almost an unavoidable mathematical consequence. The fall continues, but the destination keeps receding. We are in a state of free fall stretched out forever. At the same time, we know that the current model is no longer as seamless as it once seemed. Lambda CDM has supported cosmology for about 25 years, and it has proven its power many times. But the bulk flows still repeatedly come out larger than the model predicts. The dipoles do not fully match one another. Large-scale structures are pressing against the limit of smoothness that the model requires the universe to have. Every time an anomaly is corrected, some residual always remains. Something has still not been fully accounted for, and that residual does not shrink to zero in the way systematic error normally should. Behind the galactic plane, there are still structures that no optical telescope has fully mapped. Radio surveys are discovering them one frequency band at a time. Every new mass found behind that curtain of dust changes the overall gravitational calculation. Our picture still contains blank spaces, and only now are those gaps beginning to be filled in. Farther still, there are depths beyond current surveys, where the convergence problem may finally close or may continue pushing the unexplained origin of the Milky Way's motion closer and closer to the cosmic horizon, nearer to the edge of the region that any instrument can ever reach. The next generation of catalogues will move into that region within this very decade. And there, another test is waiting, a new Euclid test of the dark flow hypothesis, a hypothesis that has remained controversial for nearly 20 years. That new dataset will produce a number, and that number will either close the debate or reopen it on an entirely different level. Then there will be another anomaly, perhaps one not yet named, hidden in a dataset not yet published, in the hands of some research group quietly checking and rechecking a result that does not fully match the model's prediction. The history of this field has always unfolded that way. It is a chain of moments in which humanity seems almost to have reached an answer, only for new data to open yet another deeper layer of questions. And what is special this time is that the next survey is no longer in the distant future. It has already begun. The data are being collected right now. The next numbers are already on their way toward us from the telescopes currently operating out there. So the strangest part of this whole story is not only that Earth is rushing on in silence, or that the Milky Way is falling toward a gigantic gravitational region hidden behind its own galaxy. Stranger still is that we are living at exactly the moment when that map may be redrawn once again. It may be that in the next few years, everything will become more closed, more orderly, and the standard model will be reinforced with unprecedented precision. But it may also be that the cracks will widen, the anomalies will persist, and the universe will reveal itself to be even stranger than we ever dared imagine. Whichever way the outcome goes, both possibilities matter enormously, because when we measure the motion of the Milky Way, we are not only asking where our galaxy is going. In truth, we are using that motion itself to ask a much larger question. How is this universe really organized on its largest scales? And up to this moment, the most honest answer remains: we have understood a great deal, but not enough to say that the mystery is over. We know that we are being pulled along. We know the direction. We know part of the cause, but the rest of the story is still out there. In the dark regions, in the unmapped zones, in the structures not yet named, and perhaps at the edge of the very part of the universe we are able to see.